This is the third part of the lecture on section 1.3, the greatest common divisor in Euclid's algorithm. We want to begin by formalizing a definition we're probably all familiar with. We say that two integers a and b are relatively prime if the greatest common divisor of a and b is 1. Now suppose that a and b are not both 0, and let d be the greatest common divisor of a and b. Then the GCD of a over d and b over d is equal to 1. This statement makes a lot of sense intuitively. Suppose we started with the GCD of, say, 12 and 18, that is 6. If we divided the 6 out of both the 12 and the 18, we'd have 2 and 3, and the GCD of 2 and 3 is 1. In other words, we're saying that if you take out the greatest common divisor, there aren't any common divisors left, except, of course, for plus and minus 1. We'll consider the set of linear combinations ma plus nb just as we did in that previous proof, where we want only those linear combinations that are strictly greater than 0. As in the proof of the previous theorem, we'll select the minimum of these to be d, and we know that that's the greatest common divisor. Let's say in this particular case that d turns out to be s times a plus t times b. Now we know that d divides both a and b because it is the greatest common divisor of a and b. Therefore, the fractions a over d and b over d represent integers, and we can divide the equation above by this d, and we'll obtain this statement. Now, this must be the minimum of the linear combinations of a over d and b over d, because these are all positive integers, and 1 is the smallest possible positive integer. We can therefore conclude that the GCD of a over d and b over d is equal to 1. And this simply follows from what we proved in part 2 in the lecture. We turn now to the proof of the well-known and very useful Euclid's lemma. If GCD of a and b is equal to 1, and a divides bc, then a has to divide ac. For the proof, since we know that the GCD of a and b is equal to 1, it must be the case that we can find an m and an n so that the linear combination ma plus nb is equal to 1. Multiplying this through by c, we obtain this equation, c equals cma plus cnb. Now, it's clear that a divides the term cma. We can see the factor of a sitting right there. What about cnb? A divides bc, so it must also divide b times c times n, which is the other term here. Let's say that cnb is equal to sa. We can substitute this into equation 1, and we obtain c equals cma plus cnb, which is cma plus sa. Factoring out the a, we see that a divides c, and this concludes the proof of Euclid's lemma. We can also prove that if a is greater than 0 and a divides b, then the GCD of a and b must be equal to a. We won't prove that here because that proof is left as an exercise. We now turn to the central fact that allows us to show that Euclid's algorithm yields the greatest common divisor. Let a and b be integers, and a equal to qb plus r. This is the very kind of equation we get by applying the division algorithm. Then it must be the case that the greatest common divisor of a and b is the same as the greatest common divisor of b and r. We prove this by showing that the set of divisors of a and b is the same as the set of divisors of b and r, and therefore their greatest common divisor must be the same. Suppose that d is a common divisor of b and r. We want to show that d divides a. We begin by restating what it means for d to be a divisor of both b and r. D times some quotient is equal to b, and d times some probably different quotient is equal to r. A is equal to qb plus r. Substituting our expressions for b and for r into this, we see that a d can be factored out. Therefore, d is a divisor of a as well. Well, if d is a divisor of both b and a, it is a common divisor of a and b. Suppose now that d is a common divisor of a and b. We begin by solving this equation for r. Since a is divisible by d, there must be an integer p1 so that p1d is a, and similarly an integer p2 so that p2d is equal to b. We can substitute these into this equation. Since d is a common divisor of both a and b, there have to be integers p1 and p2 so that p1 times d is a and p2 times d is equal to b. r then is equal to p1d plus p2d. We can factor the d off, and we see immediately that d divides r. Therefore, if d is a common divisor of a and b, it is also a common divisor of b and r. We've thus shown that the set of common divisors of a and b is exactly the same as the set of common divisors of b and r. Consequently, the maximum of these two sets is the same since the sets are the same. Well, that is telling us then that the GCD of a and b is equal to the GCD of b and r. But that's what we were trying to prove. Let's think now about how the Euclidean algorithm works. When we are trying to compute the greatest common divisor of a and b, we'll first apply the division algorithm, and we can say that the greatest common divisor of a and b is the same as the greatest common divisor of b and r. Then we promote the b here and the r1 here, and now the greatest common divisor of b and r1 is the same as the greatest common divisor of r1 and r2. Eventually, we reach the final stage of the solution, where we'll be saying that the greatest common divisor of an and rn minus 1 is the same as the greatest common divisor of rn minus 1 and rn. When we reach that final step, the greatest common divisor of these two values is obvious. That's because the very next remainder is 0, which tells us that this remainder divides this remainder, and therefore the GCD of these two remainders is Rn itself, which is exactly what we claim in the algorithm. The formal statement of the proof, of course, translates this ... to a proof by induction. But the essential idea is all here. This completes our discussion of section 1.3 on the greatest common divisor in Euclid's algorithm.